we're going to continue Unit 3.5 and 3.6, and we're on question number 5, and it says sketch the graph of the function using the extrema, which means we need to find the critical points. We'll also go ahead and find the test points because it's going to talk about points of inflection. We want to find the x and y intercepts. We want to find horizontal, vertical lines of symmetry. If there are some, we want to find asymptotes, horizontal, vertical, and slant asymptotes, if there's those. So we want to find everything possible. When we do the extrema and the points of inflection, what we're going to do that is go ahead and find the first and second derivative and build that table like we saw. And we'll make a chart of that so we can find all those values and then we'll graph. So it's going to take a lot of room. We can't do 5, 6, 7, and 8 on one page. We probably can't just do 5 on one page. So we're going to need notebook paper here to take notes on. And I'm going to just white out these numbers, and we'll probably, I'm just going to white out my lines so I won't have to stay in lines, and then I'll probably fill this up 2 or 3 times. So we'll do a little in erase, and you'll have in your notes what we're going to do. So if you're watching the video, and you might want to be taking notes as you watch this piece of video because all of the material is not going to stay on the board. Okay. We want to find the extrema, we want to find the intercepts, we want to find the asymptotes. So let's just first of all talk about an asymptote. How do we know where there's going to be a vertical asymptote or a line of symmetry, which would be kind of the same? Where's there going to be a vertical asymptote? Okay, so let's talk about that. I'm just going to write down vertical asymptote. I always spell it wrong. I always spell it wrong. Sorry, asymptote. That's where there is a division by 0. Or the square root of negative. It's going to create an undefined situation, and in that situation there would be an asymptote, or there would be some disappearance. So we realize then if we figure out where there's a division by 0 error, if the denominator x plus 9 was equal to 0, then that would create a division by 0 error. So if we subtract 9 from both sides, we would get x is equal to negative 9. So that tells me that there is a vertical asymptote at x equals negative 9. Okay, now horizontal asymptote. How do we know if there's a horizontal asymptote? If the degree of the numerator versus the degree of the denominator so we're going to compare the degree of the numerator to the degree of the denominator. I'm just going to write all this out so we'll have it in our notes. Okay? Now, if the degree of the numerator is higher in a minute. What does that mean? It means that there's no horizontal asymptote. If the degree of the denominator is higher, it means that there is a horizontal asymptote, and it's at y equals 0. I'll spell
higher greatly this time around.
If the degree of the numerator is 1 higher, then what does that mean? Slant asymptote. Now, it's still higher, which means that there's no horizontal asymptote. But if it's 1 higher, there's a slant asymptote. And how do you get the slant asymptote? It's going to be y equal the numerator divided by the denominator, and you scratch out the remainder, right? So you take the numerator divided by the denominator using long division, and you disregard the remainder, and that is the equation for your slant asymptote. Okay? So we'll talk about this again. To find a vertical asymptote, we're going to be looking for places where there's a division by 0 error, or where there's a square root of the negative. Those are the situations where the domain is undefined. The square root of the negative, you realize, may just kind of dead-end it, right? Not necessarily a vertical asymptote. So we're going to be focusing on a division by 0 error to find a vertical asymptote. A division by 0 error would be, it would happen when the denominator becomes 0. So we set the denominator equal to 0, and we find the equation for the vertical asymptote. To find the horizontal asymptote, we know that if the degree of the numerator is higher than the degree of the denominator, then there's no horizontal asymptote. If the degree of the denominator is higher than the degree of the numerator, then there is a horizontal asymptote, and it's going to be y equals 0. If the degrees are the same, if the degree of the numerator is the same as the degree of the denominator, then what's the case? It's going to be y is equal to the ratio. Let's say that this was something x squared over something x squared. Then if the degree of the numerator is the same as the degree of the denominator, then the horizontal asymptote is going to be the ratio of leading coefficients. So we would take the leading coefficient here, the leading coefficient here. That ratio becomes our horizontal asymptote. If the degree of the numerator is 1 higher than the degree of the denominator, then there's going to be a slant asymptote. And to find it, we take the numerator divided by the denominator using long division, disregarding the remainder. I'll let everybody get that written down, and then we'll go through and find our horizontal and slant asymptotes. Then we'll get into the x-intercept and y-intercepts. Then we will find the first derivative and second derivative, identify our critical points and test points, choose our intervals, and build that little chart. Okay? Everybody good? Okay, it's going to disappear, so we have to be good. Okay, so in this situation, the degree of the numerator is bigger than the degree of the denominator. Since the degree of the numerator is higher, then there is no horizontal asymptote. Okay? So for horizontal asymptote, we would put none. All right. Now, the degree of the numerator is 1 larger than the degree of the denominator. See that? The degree of the numerator is 1 higher than the degree of the denominator. Therefore, there's a slant asymptote. And to find the slant asymptote, we're going to take the numerator divided by the denominator and disregard the remainder. So we're going to have to take x squared divided by x plus 9. Now, remember when we do long division, we put zeros as placeholders, right? We take the largest exponent, work our way down. So we would have plus 0x plus 0. We need to put those zeros in as placeholders, do you recall? Now, remember to divide, we say, how many times will the first little piece go into the first little piece, right? So we would say x goes into x squared, x times. So you see how many times it'll go. What's the next step? Good. So you see how many times it'll go, then you multiply, but we remember when we multiply, we have to distribute, right? We distribute. And that's going to give you x squared plus 9x. Right. So we see how many times it'll go, and then you multiply, and then you subtract, which you do that in the way of changing the sign, as you said. So we subtract in the way of changing the sign. Those cancel, and now we have a negative 9x. What do you do next? You bring down. So we bring down the 0, and then we start again. Now remember, we only look at first piece with first piece. So we say, how many times will the first piece x go in the first piece negative 9x, and it will go negative 9 times. And then we multiply and get negative 9x minus 81. We subtract in the way of changing the sign, which makes those cancel, and we have a remainder, of 81. Now, we would usually say, okay, then that means that it's plus 81 of those little x plus 9, right? But we disregard that remainder, so my equation is y equal the x minus 9 portion, disregarding the remainder of 81, which would really be 81 over x plus 9. Okay? So that's our slant asymptote. Now, it's been a while since we've done that. Okay, so we found our asymptotes. We got a vertical asymptote at x equal negative 9. I'll just put these all in yellow right quick. Vertical asymptote, x equal negative 9. There's no horizontal asymptote, and the slant asymptote is y equal x minus 9. So y'all can save that. It's all going to disappear from my screen, and we'll go back and retrieve that later. Now we want to talk about intercepts, okay? But good with the asymptotes. Okay. Okay, now to start again, we'll use this screen several times here. All right, x-intercept. How do you find an x-intercept? It's x when y is 0. So we're going to take our equation. We're going to put a 0 in for y. And we'd solve for x, right? Now, the easiest way to do that probably is think of this as a proportion and then cross multiply. So x plus 9 times 0 is 0. And 1 times x squared is x squared. That kind of cleaned that up pretty fast there. And then we get rid of the square with the square root, and the square root of x squared of 0 is 0. So my x-intercept is 0, 0, the origin, okay? So I'll highlight that in yellow. We found that the vertical asymptote, we found there was no horizontal asymptote, we found the slant asymptote. We found the next intercept. We want to find the y-intercept. To find the y-intercept, what do?
Set x equals 0.
Good. It's y when x is 0. So we would take our equation and put a 0 everywhere there's an x and solve for y. So we would have y equal 0 squared over 0 plus 9. Which is 0 over 9, and 0 divided by any number is 0. So the y-intercept is the same as the x-intercept, which is the origin, again. We've got the vertical asymptote, no horizontal asymptote, slant asymptote, and the x and y intercepts. Let's see what we got that for. Now what we want to do is begin to talk about critical numbers and test points. We want to find relative maxes, relative mins, points of inflection, right? And the way we're going to do that is find the first and second derivative. Once we find the first and second derivative, we'll have the critical points and test points. And then we'll divide the number line, the x-axis, into those little regions. And once we divide it into those regions, then we will test the points within that region, and we will build that chart, okay? All right, here we go. Let me just click maybe and get rid of that. There we go. Okay, so we want to find the first derivative, and we will be using the chain rule. The chain rule says you take the, what does the chain rule say? You take the denominator times the derivative of the numerator and then minus. Wait a minute.
That's
So-
not the chain.
I mean, I said chain rule,
Yeah.
didn't I? I'm sorry I said chain rule. Sorry I said chain rule. We're talking about the quotient rule. Sorry about that. Quotient rule. There we are. And that's why I got silent. Quotient rule. Denominator, x plus 9, times the derivative of the numerator, 2x, minus numerator, x squared, times the derivative of the denominator, which is x, right? 1. Over the denominator, x plus 9 quantity squared. Okay. Denominator times derivative of numerator minus numerator times derivative of denominator over denominator squared. Okay. So now we need to look at the first derivative and think about what factoring opportunities we have. What could we factor out of that? Looks like an x. Just an x, right? So we can factor out an x. We're going to have y prime is equal to x times. Now, when you take that out, you're going to have a 2 times x plus 9 left, right? And then a minus x. Over x plus 9 squared. If we distribute here, we would have y prime is equal to x times 2x plus 9 minus x over x plus.
You didn't distribute the.
I didn't distribute the 2. I need to quit making mistakes on this video. Wow. Thank you. Okay, so, thank you. So we're going to have y prime is equal to x times 2x plus 18, that's better, minus x over x plus 9 squared. All right. So then we're going to have y prime is x times x plus 18 over x plus 9 quantity squared. So x times x plus 18 over x plus 9 quantity squared. And I'm going to highlight that. We kind of need to hang on to that. That's our first derivative. So we've got a vertical asymptote, no horizontal asymptote, a slant asymptote, the x and y intercepts, and we've got the first derivative. Now, our critical numbers come out of our first derivative, right? So let's go ahead and talk about our critical numbers. Before we find the second derivative. Critical numbers, how do we find those? Critical numbers are what? It's when the first derivative is 0 or undefined. What would make the first derivative 0?
If the numerator,
Numerator equals 0. What would make it undefined? Denominator equals 0. Or there's some square root of a negative or something, okay? So, if we want to find the place where the first derivative is 0, we would set the numerator equal to 0, right? So we would take the numerator, x times x plus 18 is equal to 0. And if we wanted to know where it was undefined, we would set the denominator equal to 0. Now, for the numerator to be 0, it would be 0 at x equals 0 or x equal negative 18. I don't think we have to take the time to show that working anymore. Is there anything that we could plug in to the second part, the denominator, to end up with a 0? What could we plug in here and get a 0? Well, a negative 9, right? Because they give us a negative 9 plus 9 is 0 squared is 0. And so x equal negative 9 would create an undefined situation. Okay? So we're going to have critical numbers. We're going to have critical numbers at x equals 0, x equal negative 18, x equal 9. We're going to highlight that. That's kind of important stuff. Now, these are possible whats? Maximums and minimums. And where x is equal to 0, the first derivative is 0, is a possible point of inflection. It doesn't mean it is, it means it could be, right? Okay, so we've got possible maximums and mins and a possible point of inflection. When we get to the second derivative being 0, then we really get serious about a possible point of inflection. Okay? All right, so now we want to find the second derivative. Now, to find the second derivative, we could really pick any place in the first derivative, right, that we want to solve it, or we could clean up the first derivative. It's not going to be really pretty any way you go at it. But if we were to go ahead and distribute here on this, take it one step further in the numerator, then that's probably going to be a little bit easier to take the second derivative, you see. So let's go ahead before we do the second derivative, and let's change the first derivative into, if I were to distribute this out right here, x squared plus 18x. But you don't have to do this. I just think it's probably going to be a little bit easier if you do. Over x plus 9 quantity squared. That way you don't have to do a chain when you're doing the derivative of the numerator. Okay, so I'm going to remove the stuff over here on the left, and we'll work our way through the second derivative then. Okay, so we have a quotient, and so we're going to take the what? Denominator, which is x plus 9 squared, times the derivative of the numerator. Now we're going to put it in parentheses, right? Times the derivative of the numerator, which is going to be 2x plus 18. And then what? Minus, good. the numerator, x squared plus 18 x times the derivative of the denominator, and the derivative of the denominator would be, now that's a chain, right? Let me remove some stuff. I've got too much stuff here. I'm going to have to move my critical numbers. Okay, so we're doing times the derivative of the denominator, which is a chain, right? So to do the chain, we say exponent times coefficient 2, and then reduce the exponent by 1, so we have 2 of the guts to the first, right? But then we have to say on the chain times the derivative of the guts itself, which is times the 1. Okay? You got that? All over the denominator, x plus 9 squared, right? So we have to square that, and it was a square, so square squared is to the 4th power. Okay? Let's see how we got to there. Now, we want to try to find common factor where we can factor out a common factor. And if you look at these two terms, you're going to see that they both have an x plus 9 to the something. Now, these two factors don't match, but this does, right? Now, we could think of this as a 2 times x plus 9. If we go back and think of it like this, and this is an x times x plus 18. If you look at it like that, then really what you've got over here on the first one is an x plus 9 to the 3rd, right? See that? So let's go ahead and put that together before we get, because I want to find all the common stuff. Let's go ahead and deal with that. So let's rewrite that as y double prime is x plus 9 raised to the 3rd. I'm just going to put the 2 out here. So y double prime is 2 times x plus 9 to the 3rd minus, and let's just leave it like this, minus x squared plus 18x. I'm going to put the minus 2. Let me put that 2 out here. So minus this 2 over here, I'm going to grab that 2 of those x squared plus 18x's times an x plus 9. This might help us see plus 1 over x plus 9 raised to the 4th. Okay. Okay, so what can we factor out then? We can factor out, we've got this now, an x plus 9 to the 3rd. And there's an x plus 9 to the 1st. So we see we have a common x plus 9. And we've also got a 2 here and a 2 there, right? So we can pull out a 2, and we want to pull out the highest or the lowest. We factor out the greatest common factor. So we pull out the lowest, right? What they have in common. Okay? So we're going to pull out, we got y prime equal, we can pull out a 2, and we can pull out an x plus 9. And inside from the first chunk, we're going to have an x plus 9 squared. And on the second chunk, we pulled off the 2, so we're going to have a minus x squared plus 18x. And this is all over x plus 9 to the 4th power. Okay? Now I'm going to take the first derivative out of the way. We're done with the wheel. Okay. Now, we're going to deal with what's in here. And the way we're going to do that is we're going to do this exponent, and then we're going to distribute that. And this one is going to go with this one and make that a third power, right? We understand that those are going to cancel. So let's just go to that, do all that stuff right now. I'm going to take the top off of this. Okay, so I've got y double prime equal. I've still got my 2. My x plus 9 and my x plus 9 to the 4th made an x plus 9 to the 3rd at the bottom. When I multiply this by itself, I get the first one squared, right? Plus double the product of them. 9x doubled is 18x plus the second one squared. That's how you square a binomial. I'm just going to leave that pencil out. I didn't mean to. Are y'all good with that? When we did x plus 9 times itself. And then we're going to distribute that. We're going to have a minus x squared minus 18x. Okay? See what we got to there? Okay. All right, I'm going to wipe out the bottom. Okay, we'll find like terms to combine, so we're going to have y prime equal to times this x squared and the minus x squared. The x squares go out. So the x squares go out. There's an 18x and a minus 18x, and they go out. So now we have a 2 times an 18, which is a 162 over x plus 9 cubed. And that's not what I
You
got.
said 18, but it was 81. But that
Is 81. Yeah. We didn't make a mistake. I could have made a mistake on my key the first time. I'm not getting the same thing. My x squares didn't cancel out the first time, but I could have made a mistake because I actually did the derivative a different way. So regardless, it's going to give us the same result. I'm not real sure why I get a different numerator, but the same result is going to be here. And that result is that in the second derivative, if I want to test one, I want to find out whether the second derivative is equal to 0, right? And so to do that, are undefined, right? And so if x was equal to -9, it would create an undefined situation for the second derivative, okay? So I didn't get anything additional because I already had the -9 from the first derivative, okay? All right, everybody good there? So what we've done is we have found the second derivative. And we found a test point, which is the same as one of our critical points, right? Now, what we want to do is we want to kind of make that little chart that we saw in the video. Watching this video, and we were watching a video of the calculus being presented by Dr. Dana Mosley. Okay? He did a super job, and then we're watching those, and then I'm presenting these, and then we're doing the work. Okay, so now we're going to go and try to build our little chart. To build that chart, remember we had the test, the critical numbers. Our critical numbers were what? They were x equal negative 18, if you go least to greatest, x equal negative 9, and x equal 0. So remember what we did is we said, okay, we're gonna go x equal negative 18. Well, we're gonna divide into intervals. We're gonna say x is between negative infinity, so negative infinity is less than or equal to x is less than or equal to negative 18. And then we're going to look at x is equal to negative 18. And then we're going to say x is between let me take the equal to's off. X is equal to negative 18. Then we're going to say x is between negative 18 and negative 9. And then we're going to say, well, x is negative 9. And then we're going to say x is between negative, I'm having trouble. X is between negative 9 and 0. And then we're going to say, well, x is 0. And then we're going to say x is between 0 and positive infinity. And we're going to want to find f of x for the actual critical numbers in case it's a relevant max or min. We're going to find f prime of x. And there we're just going to determine whether it's positive or negative, right? And then we're going to take f prime of x, double prime of x, determine whether it's positive or negative, and then we're going to reach a conclusion based on our findings. Okay? Okay. Now, we want to pick something within that interval, this interval of negative infinity is less than or equal to x, which is less than or equal to 18. If we were to plug in f prime of negative 20, so on this one, I'm doing f prime negative 20 for this interval, the first interval. F prime negative 20, and I've calculated that. We just plugged it into f prime. If we plug it in, you end up getting a positive over a positive, which is positive. Okay? And you can just plug the numbers in. You know how to do that. Go back to your first derivative, plug in something that's within that interval. I chose negative 20 because it's between negative infinity and negative 18. I ended up with a positive over a positive, which is positive. Okay, and then when we plug in the negative 18, we'll do that in just a moment to get an exact point. If we plug into the second interval, I'm going to choose something between negative 18 and negative 9. So I plugged in the negative 10. When you plug in a negative 10, you're going to get a negative over a positive, which is negative. So in this second interval, the first derivative is negative. We're going to go to the third interval of negative 9 to 0. Between negative 9 and 0, I just chose negative 1. We end up with a negative over a positive, which is a negative. So in the third interval, there's a negative. In the fourth interval, between 0 and infinity, I chose a 1. You end up with a positive over a positive, which is a positive, okay? And we can plug those into the derivatives. I'm not going to be that concerned about the value at negative 18 or negative 9 or 0 unless it's a critical number. I already know the value of x at 0, right? Because we already figured that out. The value of the function at 0, x at 0 is 0, right? We already know that. Because there's an x-intercept and y-intercept at the origin 0, 0. So I can go ahead and do that. If x equal negative 18 or x equal negative 9 is a relative max or min, I'll want to plug in to the function and find that value. Okay, we can do that in just a moment. Okay, into the second derivative now. I hope I'm not, this isn't challenging to keep up with. If you're watching the video, you just obviously have to pause. If you want to go back and verify this positive negative thing, go back to your first derivative, plug in something in the interval and go from there. Okay? Now, if we look at the second derivative, in the second derivative, if I plug in okay, that's enough for one video. We're just going to stop and we'll finish this problem on the next video. You can see that this is a long process. In the next video, we'll go ahead and find out what's happening in the second derivative, and then we will reach our conclusions. If we conclude there's a relative max or min, we'll go back and we will find the function values at those points. All right? Thanks a lot.